Hi, this is Mrs. Vrobel. This is Chapter 8, Covalent Bonding, Part 4. So in this video, we're going to look at what we call a Vaspur bonding theory and how it applies to molecules. We're going to actually predict the shape of a molecule based on the theory. And then lastly, we're going to look at what is hybridization. Okay, so scientists came up with a Vaspur model because they wanted to be able to figure out, just based on the molecular shape, what kind of geometry the molecule has. So what this looks at is what we call valence shell electron pair repulsion. So the electron pairs that are around a central atom, they typically want to arrange themselves in space so that they minimize repulsion. Because please remember, electrons are negatively charged, and if they get too close to each other, they push away from each other. The other interesting thing is if there are unshared electrons, if they're non-bonding pairs, they have an effect on the shape of the molecule. Okay, so as we said, electron pairs, they tend to repel each other and they cause the bonds to be pushed in the opposite direction. And like I said, when you are looking at unshared pairs, you want to think about how does that affect the shape of the molecule, because I'll go back to that every time when we have unshared pairs. And please remember that the electron pairs are going to move as far apart as they can possible just to minimize repulsion. Okay, this is actually from your book. This is page 263. So here they show you the different types of arrangement of atoms. Notice that if we're looking at linear, we're looking at one central atom and two atoms opposite of it, and they form a 180-degree arrangement. Here we have one central atom and we have three outer atoms, and together they have three covalent bonds, and the bond angle is about 120. And then here, lastly, we have tetrahedral. So we have one central atom and we have four surrounding atoms with a total of four covalent bonds, and it has a bond angle of 109.5. This is continuing on the same page. Here we have something different. Okay, and this is where I was referring to the unshared pair of electrons. And they kind of look like ears. These are essentially electron pairs that are not covalently bonded to another atom. And as a result, look at how much space they take up. So this one pair of electrons has pushed these three covalent bonds down in another area of the atom. And as a result, the bond angle is 107.3 adjacent to each covalent bond. And notice here, this is water. Water kind of looks like Mickey Mouse ears. These two non-bonding pairs push those other two covalent bonds down further away, and as a result of it, those two covalent bonds are 104.5 degrees apart from each other. So they're very close to each other. Okay, these are further examples of molecular arrangements. So trigonal bipyramidal, you have one central atom and you essentially have five outer atoms. And then octahedral, we have one central atom and we have six outer atoms. And we'll look more at that when we do a lab with molecular shape. Okay, so you've noticed that the atoms that are covalently bonded, they arrange themselves in space around the central atom. And what is happening is a process called hybridization. So hybridization, atoms do this to lower the energy levels that they need in order to form covalent bonds. So what happens is that central atom, such as carbon, it wants to covalently bond with other atoms, and it decides to hybridize or mix these different type of electron clouds so that we have one type of electron cloud for each bond. So as a result of it, you've heard of the S and P orbitals. together they mix to form an sp3 orbital, and that sp3 orbital is used in a covalent bond. Just to let you know, lone pair electrons will also occupy hybrid orbitals. Okay, there's a term which we call electron sites, and you may hear me using it to help figure out the shape of a molecule. So an electron site is essentially we're counting the number of sigma bonds that are found around a central atom. So if you see me counting covalent bonds, I'm going to count a sigma bond as 1. Now, electron sites, we also have to count non-bonding electrons or unshared electrons, and we, as a result, call that one electron site. Now, the confusing thing is with double bonds, we don't look at the pi bond. The pi bond does not factor into the electron site, so it does not necessarily determine the molecular shape of the molecule. Okay, so for electron sites, if we have sigma bonds plus unshared and together they equal 4 total, notice that the hybridization is sp3. And this will make more sense when you see it in the lab when we're making molecules. If we have a sigma bond and unshared pairs and there's only 3 of them total, we have hybridization, which is sp2. If we have a sigma bond and unshared pairs and together they only equal 2, we call this sp1 hybridization. And then you could have an example with a sigma or unshared pair only equaling 1, and we call that S, and that's not hybridized. Okay, so shape. Why do we care about shape? Well, shape actually determines how molecules arrange themselves in space. And it also helps when we look at attractions between molecules. So when you're looking at shape, if you just have one central atom and it's bonded to another atom, it's always going to be linear. So if you have 2 atoms together, we're talking about a linear shape. The interesting thing, and this is something that you're going to have to remember, is that if you have no non-bonding pairs, so that means there's no unshared electrons, the shape will always be the same as the geometry. And I'll talk more about that in class. Okay, so shapes, and these are things that you can find when you're looking at the table in your book. That's the page 263 that I was talking about. So if you have sp2 hybridization, you're going to have planar triangle. sp2, also you'll have bent, and I'll show you an example of that eventually. sp2, you can also have linear shape. sp3, notice that there's 4 different versions. So if you have no non-bonding pairs, it'll always be tetrahedral. If you have 1 non-bonding pair, it'll be pyramidal. If you have 2 non-bonding pairs, we call that bent. And if you have 3 non-bonding pairs, we call that linear. And when you see this in the drawings and the lab that we're going to do, this will make more sense. Okay, so here we have an example of CS2. And if you remember from our naming, this is carbon disulfide. So I'm going to put carbon in the middle, and I'm going to put sulfur on either side. Now notice I have pi bonds, and we said that pi bonds do not factor into the shape of the molecule. The other thing is there are no unshared electrons that are on top of carbon, and we're just looking at carbon. We're not looking at sulfur. So this second pi bond on either side does not factor into the shape. And as a result of this is linear because we have 2 sigma bonds, and those 2 sigma bonds help to share or shape it into 180 degrees. Okay, so in summary, the Vaspur model states that electron pairs repel each other, and as a result, they will push bonds into certain regions of space in order to minimize a repulsion. And you might notice that the more non-bonding pairs you have on a central atom, the greater the push away from the electron pairs, and it shortens up the bond angles. And then lastly, hybridization is essentially the mixing of the atomic orbitals to create electron clouds that are receptive to covalent bonding.